Oh goodness. Yep. Cool. Recording in progress. All right. So spend a bit of time on primordial black holes as dark matter. Look at the physics and their constraints in a bit more detail than usual. And then we'll get into sort of the bulk of the talk, which is looking at how do we actually model black holes in a cosmological background, and what's the sort of phenomenology of a particular choice of one of these solutions. And there's quite drastic consequences to the phenomenology of primordial black holes as dark matter candidates. So let's get into it, I guess. I'll start with the dark matter. So primordial black holes are an exciting dark matter candidate for a lot of reasons. There's a good paper by Sebastian Kless and others that summarizes sort of lots of different astrophysical observations that make more sense with primordial black holes. But primarily, it's the only dark matter candidate that we've actually observed through gravitational waves and these large baseline interferometry images. And intriguingly, it's sort of hard to explain now some of these observations as stellar black holes. There's this thing called the pair instability mass gap, where a sufficiently large star, sort of roughly in this 50 to 150 solar mass region, although that's a bit controversial perhaps, it will produce more efficiently electrons and positrons, and then that will just explode the star and it won't leave any remnant. So it's hard to produce black holes in that mass range. And it seems like we're seeing them. So the question is, are these primordial in origin? Are they formed in the early universe? And the way this works is that you have some over-dense region in the early universe, and it's sort of horizon sized. As it comes back into the horizon, the mass of this overdensity, if it's large enough such that its Schwarzschild radius is the horizon size, then you can say it will collapse into a black hole with the horizon mass and some sort of numerical factor that accounts for the collapse details, usually considered to be about 0.2. And the usual mechanism for this is inhomogeneities. They get blown up during inflation. And as they come back in the horizon, they collapse. But there's all sorts of interesting mechanisms you can come up with: cosmic loop things, domain walls, exotic processes. But for the moment, we'll sort of talk about mostly just these inhomogeneities which collapse. And in general, we often assume that you end up with a monochromatic mass spectrum. So all the black holes are considered to be the same mass, or a very narrow mass spectrum around that. So I'll borrow heavily from two sources: Green and Kavanaugh's black hole review, and also Bernard Carr's recent black hole review, as we go through the constraints of whether these black holes can actually be dark matter. And luckily, as opposed to other dark matter candidates, the only real thing we have to worry about is the mass. So we get to use the second axis to keep track of the fraction of dark matter that's in primordial black holes, which is something you don't get to think about with other candidates. And this is a general plot of all the kinds of constraints, from the largest masses up to the smallest ones we care about. And I'm going to sort of go back through them from the largest to the smallest. And the thing that I'm going to try and keep in mind in blue text is, what of these constraints rely on early universe calculations, when it's sort of impactful that these black holes are actually in a cosmological medium and need to be sort of described more carefully with that. And it turns out there is a lot of these constraints that rely on that. So up in the largest mass scale are these so-called stupendously large primordial black holes, so really huge ones. And there's a number of observations which can constrain these. So for example, they will have friction within the galaxy and they'll sink towards the center and merge into a ridiculously large black hole in the center, which is not what we observe. If they sort of are hanging around in between galaxies, they'll distort galaxies. They will also cause the Milky Way to accelerate faster than it seems to be. So we have the CMB dipole constraint. Interestingly, for the early universe, we have this large-scale structure formation problem where you'll start to make galaxies earlier than we think they should be made if you have a decent amount of these stupendously large black holes. And finally, if there's accretion onto it, we might be able to see it in X-rays. And then the final sort of fun limit is this cosmological incredulity limit, which is pretty much, you don't want the black hole to be larger than the mass of the universe inside the universe. It is essentially just that. And so that lives down here at the really high mass range. So going down mass ranges, there's one that I've sort of informally titled the LIGO range bounds, which is roughly in the solar mass to hundreds of solar mass range. And there's a number of interesting constraints in this range. So firstly, there's these dynamical ones, which is essentially all the ways that these black holes will disrupt structures. So we've observed very wide binary stars, so they would disrupt those. You might not see as many of them. And also they would, sort of like when you shake a bag of trail mix and the heavy things go down to the bottom, they'll disrupt dwarf galaxies in the exact same way. And we don't see that necessarily. And in particular, there's a famous one called Eridanus 2, which is a very small star cluster, which my understanding is it's hard to explain if there's primordial black holes around. And these are sort of sensitive on the uncertainty level to the astronomical observations. So things like the dark matter velocity and all the other kind of things which are hard to observe. And moving on, we have these accretion constraints, which is that gas and dust fall into the black holes and we should see radiation as a result of this. A number of these happen in the early universe or sort of near the early universe. So they'll mess up the recombination stuff we see with the edges 21 centimeter line. And they'll also change the sort of CMB and isotropy structure. Of course, if they're still around today, there's interstellar gas and dust. And so we might still be able to see them in X-ray and radio. And these are sort of sensitive more to theoretical uncertainties. It's very hard to accurately model like accretion in a proper general relativistic sense. You can use these Bondi accretion things, but it's not so accurate, and it's an ongoing field, I suppose. So finally, the namesake of the LIGO range bounds is that we can see these black holes with gravitational waves, or we could see these black holes with gravitational waves. And in particular, what needs to happen is if these primordial black holes form binaries efficiently near when they're formed in the early universe, then some of them will merge today, and we would be able to see that. And we can predict how many mergers that would be or what the stochastic background of these mergers would look like. And we don't see it, and so we can place a limit. And so this relies heavily on the early universe because you need these binaries to actually form. So moving down the mass scale, we have this sort of vaguely micro-lensing range. There's a number of observations here, and the general principle is that if a primordial black hole moves in between us and a star, so maybe in the Large Magellanic Clouds or in the galactic bulge in Andromeda, then we'll see the star sort of increase in brightness a little bit. And we can set limits from the non-observation of these microlensing events. There's two additional interesting constraints from the observation of microlensing, actually, which is sort of interesting. The first is this sort of Icarus event, which is a lensing event we saw at quite high redshift. But my understanding is that if you have a compact object population in between there, the microlensing should be dimmer than it actually is. And there's also a similar thing with this supernova magnification distribution, where if you don't have a smooth sort of dark matter component, which we wouldn't here, then you get a slightly different sort of distribution than we actually observe. I'm not sure too much about these last two, but they're very interesting. Moving down again, we have the so-called asteroid mass range, because these are in the masses of asteroids. Interestingly, the lower bound of this is set by sort of the black holes, which are too heavy to have any effect from Hawking radiation. And those black holes are doing all their Hawking radiation in the early universe. So the lower bound of this range is early universe dependent, so I can put that in blue. And the upper bound of this range is where microlensing fails. So there used to be constraints in this range, but they've recently been shown to perhaps not actually be real anymore. So there's this even smaller microlensing called femtolensing, but diffraction effects and finite size source effects render those not possible. And you also have these interesting effects where black holes might be captured in stars and disrupt them, causing supernova, but it doesn't seem like we actually can constrain that right now. The capture rate is just too small, but maybe in the future that could be still possible. And another interesting effect where a primordial black hole which passes close by to a white dwarf might ignite some sort of carbon fusion process and blow it up. And it turns out, again, both the capture rate, or not really the capture rate, so the rate of this interaction and the physics of this runaway effect are not sufficiently well understood in order for this to actually constrain this population. So at the moment, the asteroid mass range totally unconstrained to be dark matter. So finally, there's the smallest black holes, those that evaporate quite readily via Hawking radiation. And so the most trivial constraint in this is the primordial black hole lifetime constraint, which is that at around 10 to the 15 grams, the primordial black hole evaporates within the lifetime of the universe. And this comprises what we call the stability constraint on whether these can be dark matter. Essentially, the idea is if you have a mass that's slightly more than 10 to 15 grams, the lifetime will be some multiple of the age of the universe. And if you have a mass slightly less than 10 to 15 grams, it'll just decay extremely rapidly. So it's very hard to populate today with black holes in between that range, because even if you start with some extended distribution of black holes, you'll end up with pretty much all of them being around 10 to 15 grams or having evaporated already. So it's very hard to actually say, oh, like a 10 to the 8 gram black hole has survived today. It's extremely fine tuned to have that sort of scenario. But of course, as these things are evaporating in the early universe, there's heaps of processes which they might muck up. So they'll, of course, change the shape of the CMB anisotropies. They'll mess up Big Bang nucleosynthesis. They'll produce lots of gamma rays that we could probably detect. And if they do hang around long enough to stack up in the galactic center, maybe they'd produce more positrons than our observations allow. So we can place sort of narrow constraints that way. So I guess sort of a review. What is the areas of interest for cosmological primordial black holes? So those constraints in blue, where would they most show up? And so the first one is in this asteroid mass range and the evaporation range, where this lower bound here all takes place in the early universe, all these evaporation processes. And secondly is this sort of LIGO range, where a number of those processes took place in the early universe, the accretion ones and the gravitational wave ones. And also sort of depending who you ask and how seriously you take the uncertainties in these measurements, there may be a slim possibility that you could get all the way up to 1 here if these things even shift a little bit. So that's an exciting place to look, and especially because we've observed those black holes. So let's talk about these cosmological black holes in more detail. So there's an interesting history with describing black holes properly embedded in cosmology. And it started with Zeldovich and Novikov, who showed that if you just had a Schwarzschild black hole in the early universe, it would accrete ridiculously quickly and blow up to massive sizes. And so they actually dismissed the concept of the primordial black hole outright in this paper in 1966. It was only when Bernard Carr and Stephen Hawking showed later on that you need to have a proper cosmologically embedded metric, which is asymptotically FLRW, so it's like actually cosmological at long distances, that you can escape this runaway accretion problem. And then I'm not really sure what happened to this field. It seems like this idea that you need a proper cosmological metric was sort of pushed to the wayside as we got excited about other things. But there's on top of this runaway accretion problem, there's some sort of obvious reasons why you can't use the Schwarzschild metric anymore. I mean, trivially, it's not sourced correctly. It's embedded in flat empty space, and you have to define the mass as an inertial observer at spatial infinity. And you can't do either of those in cosmology because there's a hot, dense cosmological fluid around you. There's a Hubble horizon, which, especially when the black hole's formed, is perhaps not very far away from the black hole horizon. And on top of that, we'll need a local mass definition. So something that's not this idea of an inertial ADM mass at infinity. In general, there's sort of a convenient way to write spherically symmetric metrics, and that's using this almost Schwarzschild looking form. If you just take any spherical symmetric metric, you can do suitable coordinate transformations and get it here, essentially. Here, this quantity MMS is known as the Misner-Sharp mass. This is a coordinate invariant measure of internal energy, which is sort of easy to see in this coordinate system. You can just use the Einstein equations to quickly show that the Misner-Sharp mass is just sort of the energy within some volume. So it has a relatively simple interpretation in this coordinate system. This is a sort of well-known quantity. It's a quasi-local and effective description of mass. which is exactly what we're looking for a cosmological metric. An interesting problem with dynamic metrics of any kind, where this Misner-Sharp mass is not just a number, but it's the actual function of R and T, you no longer have a killing field, which makes it hard to define things like surface gravity and forward acceleration. But luckily, there's a sort of analogous field called the Kodama vector, which defines a time-like direction. And in the static limit, it doesn't exactly go to the killing field, but it's parallel to it. And then it was shown relatively recently that this Kodama vector defines a geometrically preferred time coordinate, which is the one we've chosen here, in fact, that puts you in this nice form. And we've actually made an extra assumption here that the norm of the Kodama time translation vector should coincide with the norm of the Kodama vector itself. And that sort of simplifies this time term here. And that's actually the same thing you would do with the regular Schwarzschild metric when you're talking about the killing vector and the regular time translation vector. And so when we're in this sort of coordinate base, there's a less ambiguous definition of surface gravity and forward acceleration, although you still get some choice with the normalization, as I was saying there. But let's look at some particular actual cosmological solutions. So metrics which have a central inhomogeneity, but are asymptotically FLRW. So this is like a well-studied piece of literature, perhaps could be more well-studied, but there's a number of solutions, but a lot of them don't serve our purposes. We need to be able to describe black holes in radiation domination, so in the really early universe when they form, and we don't want it to have any space-like singularities, which lead to negative energy densities and other kinds of pathologies. And a lot of the ones proposed over the years are not suitable for this, and are one or two or either of these problems. So the most famous one is maybe this Einstein-Strauss solution, the Swiss cheese vacuole, which just takes a Schwarzschild solution and just stitches it into FLRW at some radius. But if you want to match the pressure conditions properly at the boundary, it needs to be in a dust background, so it's not useful earlier on. The other sort of famous one is this McVitie solution, which is very old, I think from the 1930s. But this one, unfortunately, has a space-like singularity at its horizon. It's pretty much a very general central inhomogeneity sourced by a perfect fluid, just like the FLRW metric. But it was realized that you can escape this space-like singularity by removing the assumption that it's sourced by a perfect fluid and giving it an imperfect fluid. So it has some sort of radial heat flow or radial matter flow. And in particular, when you generalize the McVitie metric in that way, there's a specific late time attractor solution known as the Thakurta metric, which doesn't have any singularities. It works perfectly fine in radiation domination. So for, I guess, the rest of this talk, we're going to say this is the best metric we could find so far. And we'll see what the phenomenological implications of this metric are for primordial black holes as dark matter. So as I was saying, the Thakurta metric is the attractor solution of these generalized McVitie metrics. But importantly, it's actually quite simple. It's pretty much just the cosmological scale factor times by the Schwarzschild metric. And when you calculate that explicitly, you end up with this kind of metric, which has these radial terms because it has a radial heat flow, which sources it. And in this case, this M here, this parameter, we interpret as sort of the physical mass of the overdensity that formed this black hole, or you could also think of it as the mass in the static limit as measured today. Is that a question or no? I think not. Okay. Ooh, sorry. So right, as I was saying, this is sourced by a perfect fluid, but now it has a radial heat flow component and no radial matter flow to source the Thakurta metric. But we would like to have the Thakurta metric in that sort of general spherically symmetric form in terms of the so-called Misner-Sharp mass. And you can do that with a particular transformation. It's not super hard to work out. And one thing that's interesting is that away from both the horizons, the black hole apparent horizon and the cosmological one, these times roughly coincide. So when I go to this Kodama time metric, I don't have to worry too much about messing around with the scale factor time parameterization. I can just call them the same as what I usually would with the Friedmann equations. And when you go through the work and you actually figure it out, we can find the Misner-Sharp mass explicitly, which looks like a sort of co-moving term, and this secondary term, which depends on also the Hubble rate. So we'll look at that in more detail in a second. One thing to note is that this black hole has a so-called apparent horizon, or a trapping horizon, which we can solve exactly analytically, which is sort of rare for these solutions. It's just a case where you set this thing equal to 0. And in this case, this apparent horizon conveniently defines a small parameter for us. So this is always true after the black hole is formed, which will be very useful for all of our calculations. And you can even write the apparent horizon in this form. It pretty much looks as you would expect, like 2MA, which is, well, I guess I should put a G there, 2GMA, which is the same one with the scale factor. But let's look specifically at the interpretation of this Misner-Sharp mass. And it's sort of interesting to look at the two sort of extremes in the radial direction. So when R is above or below this sort of value, which is just when these two terms are equal to each other. So when you're below that, this term dominates, and the Misner-Sharp mass essentially just looks like a co-moving mass. And when you're above this sort of radius, the Misner-Sharp mass goes to the right-hand term, and you can use the regular Friedmann equations, because we're far away from the black hole, to write h squared in terms of rho, the total energy density, which includes, importantly, the black hole itself in our interpretation. And so I guess the main point here is you have to be very careful about your physical interpretation of these two terms. It's not that this one represents the black hole and this one represents exactly the fluid around it. They both contribute at the same time to this local gravitational mass called the Misner-Sharp mass. And at large distances, we just recover the regular FLRW metric, including the black holes themselves. All right. So how do we actually model these Thakurta black holes in the universe? So as I was saying, they will still say they form from the regular overdensity as usual, but we have to keep in mind that the Misner-Sharp mass is a local effective mass. It's not applicable for global parameters, which is sort of obvious from this long distance limit of the Misner-Sharp mass. In particular, the global black hole energy density still will scale in sort of our model, our interpretation, with the number density of black holes times their physical mass m. And so it still is a viable cold dark matter candidate. And another important aspect of the Thakurta model is that it's only relevant until these black holes are decoupled in some way. What that means is when the most important part of the local dynamics of these black holes is the cosmological fluid, it's perfectly fine to describe them using the Thakurta metric. But as soon as something else dominates their dynamics that's not the cosmological fluid, it no longer makes sense to describe them with the Thakurta metric, and this description breaks down. So that would be something like the formation of binary black holes, or structure formation when they get virialized into them. And our assumption here is that once these black holes decouple, they regain, in some sense, a more Schwarzschild-like description, or something like that, with their physical mass m, as we would measure it today. And so these sort of this model of the Thakurta black holes is definitely not trivial, and is something that needs particular attention. I would say, I guess good science needs to be falsifiable. And I would say if you were looking to falsify this as a good black hole model, the thing that would be the most interesting to investigate would probably be the sort of formation process and this interpolation back into different description, as well as the multi-black hole solution. If you could somehow show that when you put multiple Thakurta black holes, that this asymptotically FLRW description breaks down, then you would probably invalidate this sort of model. All those things are probably going to be hard to do. It's generally quite difficult to write down these things in a general relativistic setting. But I guess that's the main breaking points that I think are the most interesting. But we can't find anything better, so this is what we're going with for now. So let's look at the phenomenology of these black holes. So the first thing I want to look at are these LIGO bounds, these binary abundance bounds that black holes form binaries very efficiently in the early universe. And so LIGO should detect heaps of signals, which they don't. And the idea of this is, okay, so when black holes form, they're sort of randomly distributed in the early universe. And if any two of them are sufficiently close, they'll decouple from the Hubble flow, form a binary, and then we want to model the resulting distribution of binaries. And then you can figure out what the LIGO detection rate should be. We'll assume here, again, a monochromatic mass spectrum, and that the distribution is totally random. There's no clustering or anything fancy like that. It was shown that if there is clustering, that can readily disrupt the binaries, and you might be able to escape these constraints anyway. But we won't assume that everything is just random. Okay, so how does this work? Well, we can figure out the average black hole separation today, just sort of from the number density and the fraction of dark matter. And that's this quantity here. And in earlier times, that would just scale, this sort of physical distance just scales with scale factor, as you would expect. If the black holes are close enough to decouple and form a binary, they'll get a sort of spin from the next nearest black hole, which I've called with this y distance here. And that will give the black hole binary an eccentricity, so they don't just fall into each other. So we can write down the semi-major axis with some order 1 numerical factor to account for more details. We can do the same thing with this semi-minor axis, which is just a tidal disruption of these two black holes. And that allows us to define the eccentricity. And we can write down a distribution function for all of these black hole separations in this sort of x and y space, which is given by this function here. It's not particularly intuitive looking, but I promise you, if you integrate this over x and y, you will find that it gives you exactly what you expect. So say the black holes satisfy whatever the decoupling condition is at a particular time. So z equals z decoupling or redshift. Then the black holes decouple with the coalescence time, which is a sort of well-known calculation from Peters in the 1960s. And we can use this to substitute back into this distribution function. So now it's in terms of coalescence times and eccentricities. And all we have to do is integrate over the eccentricities. And then we can find that the event rate of mergers that LIGO would measure is just the number density of black holes times by this probability density evaluated at sort of essentially the age of the universe. So the lifetime which would allow them to be merging right today. And obviously this sensitively depends on what is the decoupling condition for these black holes. In the Schwarzschild case, there's sort of easy intuition for this. You can essentially say when the mass energy of the two black holes is greater than the energy density of the fluid in the sort of volume they occupy, then they decouple and form a binary. So that's this condition here. And you can actually derive this more carefully by looking at the geodesic for test particles with a cosmological sort of separation term. And if you say that you want r dot to be less than 0, then you'll derive a similar thing to this relation. Not exactly the same, but close enough. In the Thakurta case, this is more complicated because before they have decoupled, they're described using this Misner-Sharp mass. So this first condition, which I sort of informally call the static decoupling condition, it's essentially the same, except now I have this MA term instead of just M. So that leads to a more stringent decoupling condition already. This makes it harder to decouple. But on top of that, I have to be a little bit more careful. And this is something we learned when we were investigating this numerically, trying to do a simulation of this decoupling. And we found that you need to explicitly require that the energy lost by gravitational waves is larger than the energy that sort of separates these black holes. And that's something that you get for free in the Schwarzschild case. It's trivially true. But here we have to look carefully at the sort of energy of two Misner-Sharp black holes. And we can calculate this condition so that if R dot is less than 0, this must be true, essentially. So what we need to do is work out what is the power of these Thakurta black holes, so before they've decoupled. And to this, we can go back to the classic GR calculations for power. If we assume that these black holes are in Keplerian motion, so they'll have some distance between them and an angle that sort of parameterizes this ellipse, then we can calculate the quadrupole tensor elements in this XY plane that describes their spiral, and use the sort of famous result for the power lost by gravitational waves in terms of the quadrupole moment. And if you explicitly calculate this for the Thakurta black hole, which took me a lot longer than it looks from this slide, you find that you essentially get the regular Schwarzschild power with an extra a to the 5 factor, which is quite significant, and a bunch of subdominant terms, which are very interesting. And as you can imagine, the result of this a to the 5 is that this coupling condition is very difficult to satisfy. We can take it explicitly and substitute in the power we found, and remember that once these black holes actually can decouple, they should regain a more Schwarzschild description, so they're no longer applicable to be described by the Thakurta metric. We can substitute these two relations into this decoupling condition and find a relation that tells me at any given redshift, what is the coalescence of the black hole that decouples at that time? What is the coalescence time? And so when we actually crunch the numbers, we see that for Thakurta black holes, say at matter radiation equality, the black holes which are decoupling have a coalescence time that's tiny. It's 100 seconds. It's pretty much nothing, which means that almost no black holes have decoupled at all by matter radiation equality, because these had to have been incredibly close together, which is a very small part of the distribution. Meanwhile, for Schwarzschild black holes, which don't have this sort of stringent condition, by matter radiation equality, the vast majority of these black holes have fully decoupled with extremely long coalescence time, which are sufficiently long for lots of them to be observable today by LIGO. In fact, after matter radiation equality, the Schwarzschild black holes can't decouple anymore, because in matter domination, the energy drops like 8 to the 3, and so does the distance between black holes. So they can no longer satisfy the decoupling condition. But that's not true for Thakurta black holes. They can keep trying to decouple well into matter domination, as long as they satisfy the condition. And so here's an explicit plot that shows the coalescence time of a black hole binary that formed at any given time in the universe all the way up through today. And we can see that even at z equals 1, which is way far past the early universe, these black holes don't have a coalescence time, even with a high eccentricity, to be observable by LIGO. And what we can conclude is that, galaxies are formed before this. And so these black holes actually should have been virialized in galaxies and not have formed binaries pretty much at all. Essentially an insignificant quantity of formed binaries in the early universe. And that allows us to sort of trivially escape these LIGO constraints, because the merger rate of black holes which are just virialized in galaxies is consistent with LIGO conveniently. So we put out a paper about this, and that was published a good few months ago now. All right, so let's move on to a different kind of phenomenology, and that's the other gap I was interested in, the lower edge of this asteroid mass gap, where the Hawking evaporation might be significant. In particular, I'm interested in, again, the smallest primordial black hole, which survives until today, which I'll call the critical mass black hole. And I already described this constraint a little bit, which is essentially you just can't populate dark matter today with black holes smaller than this, because you have such a sensitivity to that initial condition, this actual value of the critical mass. A tiny bit above, and you just end up with all black holes of the critical mass, and a tiny bit below, they just decay way too early. And of course, there's further effects from the CMB, from the BBN, but we can investigate this critical mass and see what that tells us before we do anything more complicated. So let's look at Hawking radiation for the Thakurta black holes. So again, this black hole horizon is the parent horizon is much smaller than the Schwarzschild one, which means that I guess you might expect they're much hotter, so they evaporate much more quickly. The sort of more formal way to look at this is to directly calculate surface gravity, which we can do. It's relatively well defined in our coordinate system, which means that our surface gravity in the Thakurta case, when you calculate it, is more or less just the Schwarzschild one divided by the scale factor with some other numbers around. After that, we'll define temperature in the standard way for Hawking radiation, which is just proportional to surface gravity. And we'll assume that the black holes radiate following the sort of Stefan-Boltzmann law for black body radiation. And this is essentially something that always needs to be added by hand because this is a quantum effect. It's not described in general relativity in any way. So we'll follow the calculation in the usual slightly ad hoc, easier way. But before we do that, we might want to check that this black hole is actually at least close to thermality because this temperature is explicitly time dependent now because the parent horizon is growing. Luckily, when we actually check that, we find that it's trivially true because we assume these black holes formed at this point. So this is always satisfied, and we can assume that we don't have any thermality problems for black body radiation. As I was saying, we'll follow the easier derivation of Hawking radiation, so not the fully worked quantum field theory equations, although I would love someone else to do them at some point, just not me. And the way you do this is you start with the sort of famous thermodynamic identity, which is pretty much just a fancy version of Einstein's field equations, but with real specific terms put in place. And the entropy is given by the surface area of the black hole, which was, I guess, the famous revelation. In our case, we can't ignore this PdV term because it's not zero, as it would be in the Schwarzschild case. And we have to be slightly careful too about the changing energy term. Usually for the Schwarzschild case, you just add the black body radiation here, but we have to take into account the fact that the apparent horizon is also growing. And so this du on dt or d tau has an extra contribution, which it turns out looks like 2 delta, where delta is that small parameter. And we can solve this thermodynamic identity for the change in the physical mass m. It's pretty much buried in these two derivatives here. So you just got to move them around a little bit. And you'll find that the change in mass is pretty much the Schwarzschild one divided by a squared. So in the early universe, when these things form, that's a significantly higher mass loss rate. So you can imagine that larger black holes will evaporate very rapidly compared to the usual situation. In particular, we want to find the so-called critical mass, which in this case I'll define by the mass which evaporates by matter radiation equality. And I'm just setting that because it's analytically tractable to do so, and because it's going to be barely different to the one that actually decays today. The vast majority of this effect is in the early universe when A is very small. So there's not going to be that much different in the critical mass between these definitions. So to do this, you just have to separate the differential equation. It's relatively straightforward. And of course, keep in mind that the formation time of these black holes is mass dependent because it's when the mass equals the horizon size. And if you properly solve this, you'll find that the critical mass sits at around 10 to the minus 12 solar masses, which is pretty much right at the upper end of the asteroid mass range, which is very exciting. And I'll show here, we can also calculate this numerically. And this is demonstrating more explicitly this stability constraint that I was talking about, which is that if you change the initial mass even slightly, you'll end up with barely any decay, or it'll decay all the way down to zero. So even if you have some complicated extended mass distribution up here, you just will not be able to populate these today because only a tiny fraction will go to intermediate sizes. The vast majority will go there or go down there. All right, so this is the result of that. You pretty much exclude this all the way up to here just by moving this left edge with a little fuzziness at the bottom because, okay, maybe you can produce those middle ones, but in tiny numbers. So it's not really a very good dark matter candidate. We investigated briefly whether you can move this edge up to here, but unfortunately, it doesn't look like you really can. And that's because these constraints happen around the time of the CMB, which is Z equals 1,000 or so. And that's not a significant enough order of magnitude to pull these, however many, 6 orders of magnitude up here. It doesn't quite give you enough. So we can't quite close that gap, but it's very intriguingly smaller than it was. So I put this one out on the archive not too long ago. So, well, we'll see if that one gets published, but maybe it will. All right, so I guess, yeah, it's about time to conclude. And throughout this project, or these projects, I guess we had 2 main things we wanted. The first was we wanted to engage the community in this sort of discussion about how do you model black holes properly in a cosmological setting, because it seems to us that there's quite drastic consequences, and it hasn't really been studied that well by the community. We really need a robust model of these and then a robust understanding of the consequences. And I'd say we have been successful in engaging the community. You've probably seen our very exciting archive dialogues, which have been great. I think that's good science, to be able to, disagree with each other and have good discussions. We chatted to them yesterday and it was productive. Who knows how this will continue? Maybe we'll just keep going forever. But I guess eventually, hopefully, we'll converge on some sort of solution, and that will be exciting. And in the other sense, we were aiming to do something more specific, which was the actual phenomenology of the Thakurta metric, which is sort of the bulk of the science I've talked about today. And there's exciting consequences here. It looks like maybe we can open up that LIGO-mass window for primordial black hole dark matter, and maybe we can close the asteroid mass window entirely. There's a lot of work to be done, though. This is only 2 of the most obvious effects we could think to check. So the accretion constraints, there's heaps of early universe ones to look at, which we're currently working on. There's lots more exotic processes, which we've thought of, but I'll hold close to my chest for now. And of course, we want a better understanding of the Thakurta metric itself. What does the multi-black hole solution look like? How do we properly interpolate? What's the interpretation of these mass terms, etc.? These are things that would be great to keep exploring and to see the community keep exploring. And finally, well, we looked at the Thakurta metric because it's the best one we could find, but maybe there's better ones. Maybe we haven't finished that game yet. And it would be exciting to see the sort of dark matter black hole community work more closely with the sort of general relativity experts to keep pushing this one forward. So that's all I have today. Thanks for listening.
Yeah. Thank you very much, Zac. Are there any questions? You can raise your hand or just speak up. Good. But maybe I start. So the Thakurta metric describes one black hole in the FLRW universe.
Yeah.
Are there any attempts to have kind of what would happen if you have 2 of the 2 black holes in an FLRW universe? Kind of when you go to the binary, right? So in the end, when you have the inspiral, they come close. So what happens there? Or what?
Well, sort of our understanding for the Thakurta metric is that you couldn't use it anymore once a binary's formed, because it's no longer dominated by the cosmological background. It's dominated by the other black hole. So whatever the solution is, it's going to be more like your 2-body Schwarzschild-ish thing of some kind. In terms of having multiple Thakurta black holes stitched together, I've never seen anyone do that. There hasn't been that many people doing that much with the Thakurta metric at all. But I guess that would be exciting. It's very hard to do these things exactly in GR.
Yeah, I can imagine. But okay, I could imagine that wouldn't it just work if they are far enough away from each other, those Thakurta black holes?
Yeah, hopefully, because they're asymptotically FLRW, the stitching shouldn't be too complicated. That would be the hope. The question of when you do that, how do these masses see each other, or how does the test particle see the masses? It's a little bit complicated, I think.
Okay, thanks. Other questions?
Hey, can you go to slide 38, please? I think there's more. Can you hear me? Probably, yeah. All right. I think you said that. I think it was there, right? That you said the Thakurta metric would increase the Hawking radiation in the earlier universe, right? So, do you know how much that would influence the gas fraction, like the gas constant in the early universe? Because if it evaporates to something, right? Is that significant or not?
Yeah, so I mean, it's an interesting question. It obviously will have a huge sort of particle outflow. This is happening like really early on though, before BBN. And my understanding is that it's very hard to put any constraints on things before BBN, because we just can't observe it, and it'll just thermalize. It probably is the case that there will be constraints from BBN on this still, but they're very complicated to work out because you have to figure out what's the like secondary decay products and how does that mess up all these like very detailed steps in BBN. So that would probably take you a whole PhD thesis to do properly.
All right, and do you know if we could see that through the neutrino background?
Can we see that through the neutrino background? Maybe.
Yeah,
I'm not a good enough cosmologist to answer that. You ask Marcus.
Probably not. So I think it happens very early.
If it happens very early, then like it would thermalize with the neutrinos as well. So
Yeah.
you wouldn't see much. Maybe if you had a perturbation to the temperature of the neutrinos, but then I think for that to have any effect, you would really need to have these black holes as sort of a baryogenesis or something, rather than just a small component adding a bit in. One of the things is also that if you want these black holes to survive until today, then they need to be so heavy that only a small fraction of their total mass evaporates early on. And thus the amount of energy ejected would have to be smaller than like the dark matter content of the universe today.
Great. Any other questions?
I actually have a question. I think we discussed this at one point before, but is there sort of an unambiguous way of defining the Mr. Sharp mass and the apparent mass and horizon in terms of the cosmological horizon, the physical distance to the horizon, rather than using the scale factor?
In terms of the physical distance to the horizon. Sorry, what do you mean?
So the scale factor is only really an expression of the size of the universe compared to the size of the universe at another point in its history. Is there a way to sort of unambiguously tie the effective mass to the cosmological horizon at a given time, so you don't have to compare two different times?
I'm not sure. I guess the problem with these cosmological things is that it's always sort of observer dependent. And I can't really tell you at any given moment, like what my scale factor currently is. I set it to 1 where I am just for convenience and calculations. I'm not sure that's different than anything else though, right?
No, but what I like, there's an actual physical process that happens in the black hole, right? It emits some amount of particles, and I think at a given time you would have to unambiguously define how many particles that would be, because that would be a physical observable, right?
Yeah, I mean, I guess the scale factor is tied to the size of the horizon at that moment, so you could read them off each other, right?
But then
You can just solve for it. So if you knew the size of the horizon, I guess you know that, right?
But then you're sort of defining it from the emission rate today, right? Because that's how the scale factor is defined usually. That is one today.
But you need to know the rate of change of the scale factor also. So there's 2 pieces of information you need here, right?
I think the question is that the scale factor by itself is ambiguous. You need to normalized to one
Yeah, exactly.
today or something like that, right?
Yeah,
I think that's taken into account.
okay, yeah,
Yeah, I mean, you can think of this A as an A on A naught at all times, right? And I've just set A naught to 1.
yeah, but so,
It's always a ratio of whatever your observer is that set it to be A naught.
exactly, and that's what tickles me a bit, because I would want to have an unambiguous definition of the emission rate at a given time that doesn't have to be compared for another time.
Yeah, I mean, if you have things that depend on the cosmology around them, I don't know how you can get around that it's depending on the time you're in, you know? It's just that's
Yeah,
right.
but maybe depend on the age of the universe, or on the.
Well, that's the same thing in another word, right?
Yeah, except you, like, it depends on the universe, but it's sort of a less ambiguous parameter it's not rescaled in the same way.
If you wanted, you could just substitute A for T, you know, where T is the time since the Big Bang or whatever you want to call it. And it would be 1-to-1 with that, you know.
Ish.
Yeah,
Yeah,
I guess you can always scale it back.
Reference time anyway, right? So that's the point what Marcus is asking. But this is the nature of the solution, right? So per se, the Misner-Sharp mass is ordinary independent. Once you have a once you have a metric, you define where it doesn't depend on the choice of coordinates and things like that. Now, here, talking about the particular process of evaporation, why it's one of the A dependent, not one of the H, something like that, it just comes out through evaporation.
Yeah. Okay. Yeah, I think.
Are there any?
Yeah.
Are there any sides that they can further exercise this? Why is one of the A?
Why is
Yeah,
like this A squared?
That's right. The temperature eventually is one of the.
Yeah, I mean, really the heart of it is this, right? T is like kappa, and kappa goes like 1 on A, because, well, in the Schwarzschild case, the surface gravity is just like 1 on M, and now it's 1 on MA, you know. You just follow that through.
Okay.
Yeah, I think what I wish for is an unambiguous definition from observables, so to speak.
Yeah, you want to see it in terms of temperature or size of the physical universe at that time when it happens. Good. Any last question? So we are close to 5 o'clock. No more questions? Okay, good. Then let's thank Zac again for a very interesting talk. And people who have to leave can, of course, leave, but other